This video, I'm going to work through some problems out of Chapter 5, Section 2. First, we need to identify the difference between a power function, a polynomial function, or something that's neither one. A power function, basically, when you're looking at the equation, for a power function, you're going to have the variable raised to some kind of power where the power is a number. It's a constant. If you don't have that, then it cannot be a power function. Now, it may have a constant multiplied out on the front of it, but basically you have to have some kind of x, your variable, raised to some kind of number power. Now, you could have some kind of coefficient at the front, and that's okay, but you can't have the variable showing up anywhere else in the problem. So when we're looking at this example right here, notice that the variable is right there in that power. That makes it not a power function. Now, polynomials are sums and differences of power functions, so it can't be a polynomial either. So this qualifies as a neither. It is, in fact, what we call an exponential problem because the power is in the exponent. So this is actually what we'll call exponential when we get later this semester. All right, now let's take a look at the next one. The next one down, we want to identify. We have the variable x raised to the power 8. That's a variable to a number power. So this is both a power function and a polynomial. So it's kind of both. But technically, we would call it a power function. And I seem to be having trouble. Hang on just a second while I fix my stylus. So x to the 8th is both a power function and technically also a polynomial. Remember that poly means many, but in the case of mathematics, it could mean one or more. Nomial means terms or things that are added and subtracted together. Let's take a look at the next problem. Find the degree and leading coefficient for these given polynomials. Each individual term, thing added or subtracted to other things, has its own degree and its own coefficient. So if I were looking just at the first term, 5, the degree of the 5 is actually 0. So this is degree 0, coefficient 5. The second term has a degree of 2, and the coefficient is 4, negative 4. So the coefficient is negative 4. The degree of the entire polynomial is the highest degree on any one term. So I would call this a degree 2 polynomial. The leading coefficient is going to be the coefficient of the term that has the highest degree. In this particular polynomial, the highest degree is 2, and the leading coefficient then would be negative 4. What about the next problem? When we're looking at the next one, I have 4 terms. Each term has its own coefficient and its own degree. The first one has degree of 2 and coefficient of negative 3. The second term has degree 5, which is bigger, and it has coefficient of negative 3. The third term has degree 1 because it is x to the first, though the power is not written, and the coefficient is also 1, even though it is not written. We could write it as 1 times x to the first power. That makes the coefficient 1. The last term is a negative 6, which is a constant. The degree of all constant terms is 0, and the coefficient is the constant, negative 6. The highest degree we see on any one term is the 5th power that we see right here, now ringed in pink. Because that's the highest power, the degree of the entire polynomial is 5, and the leading coefficient will be the coefficient on that term. So the leading coefficient is not necessarily at the front, it's always the coefficient of the highest degree term. So our leading coefficient is going to be -3. Now when we look at these and we're wondering what it looks like when we draw it, the degree and the leading coefficient give us the general shape of it. It won't give us the specifics, but it will tell us whether on the ends the arms go up or both go down, or one goes up and one goes down. So let me draw for you some examples of what that would look like. When we look at polynomials, the thing to remember about the graph of all polynomials is that they are smooth and connected. So when we look at polynomial graphs, there should be no sharp corners and no pointy parts. So here's an example of a polynomial where both arms go down on the far left and the far right. Since both arms go down, I know this means the leading coefficient must be negative. So if the leading coefficient is negative, then both arms will go down for an even degree polynomial. Leading coefficient is less than 0. What would cause them to go up? Well, it could be something like this. And again, my stylus is kind of cutting in and out. On this one, you can see that both arms do go up on the end. This one is with the leading coefficient being positive or greater than 0. Now, what makes both arms go up or both arms go down? This means the degree of the overall polynomial, not any individual term, but the whole thing, the degree is even. If they both go up or both go down, then the degree of the overall polynomial is even. If they both go down, it's even with a negative leading coefficient. If they both go up, it's even with a positive leading coefficient. What about negative degree? For negative degree, it's going to do something slightly different. So the degree is going to be odd now. We're going to have one up and one down. It could do some wiggling in the middle, but in general, an odd degree has one arm up and one arm down. Now this one is going to have a leading coefficient that is positive or greater than 0. This is because it generally, overall, from the left all the way up to the right, it generally goes uphill. If I looked from very far away, I'd say uphill. That means the leading coefficient is positive. What about a negative leading coefficient? Well, if the leading coefficient were negative, that means from far away, it would look like the overall graph is going downhill. That gives me a negative leading coefficient. This is what causes polynomial graphs to generally go uphill or generally downhill. Their degree is odd, meaning one arm up, one arm down, and generally uphill is a positive leading coefficient, generally downhill is a negative leading coefficient. Let's take a look at another problem and see if we can find the degree where it's not quite as simple as the first ones we did. In this example, we have something in parentheses. This means I've got x squared times 9x minus 9, the quantity, squared. If I were to multiply out this part of it in parentheses, the 9x minus 9 quantity squared, I would get something that was degree 2. I would also have an x term and a constant term, but the biggest I'd get out would be degree 2. So if I multiplied a degree 2 by another degree 2 at the beginning, that would give me overall degree 4. So the whole thing is going to be degree 4, which must mean that it is overall an even degree polynomial. So both arms will go up or both arms will go down. Now, how do I figure this out? From each factor, and again, factors are things separated by multiplication, not buried inside of parentheses. So when I look at the two factors that I have here, the factors are the parentheses 9x minus 9, and the second parentheses is the x by itself. When I look at these, I take the highest degree term of each one and I multiply them together with the powers on the outside. So I think of this as x squared times 9x squared. I'm going to ignore the minus 9 because it's a lower degree and it's inside the factor 9x minus 9. The 9x squared would give me 81x squared times another x squared, which would give me 81x to the fourth. The degree then will be 4, and my leading coefficient, which I can abbreviate LC, is going to be 81. That means in general, the graph of that has to look something like the one here on the right, where the two arms are going up. In a moment, we'll talk about how to know how many terms it can have, or what are called turning points. Basically, turning points are the low points and the high points on the graph where it changes direction and turns to go the other way. So if I'm looking at a graph and I'm trying to figure out the turning points, this first one on the left has 1, 2, 3 turning points. It has to be at least degree 4, one more than the number of turning points. So this could be degree 4, but it could also be 6, 8, 10, or any higher even degree. What about the one on the right? It's got 1, 2, 3, 4, 5 turning points. One more than that would be degree 6. It's not possible to draw this one with a degree 4, but it could be 6, 8, 10, 12, or any higher even degree. What about the ones below it? These were the odd leading coefficients, odd degree, and I've got a leading coefficient positive on the left and negative on the right. The one on the left has 1, 2, 3, 4 leading coefficients, which means the smallest degree would be 5, one more, but it could also be 7, 9, 11, or any higher odd degree. The one on the right has 1, 2, 3, 4 as well, so it could also be degree 5, 7, 9, 11, and so on. The distinguishing part between the two would be the value of the leading coefficient, and that it would need to be negative for the one on the right and positive for the one on the left. Let's use what we just talked about to determine the end behavior of the function x to the 10th. End behavior is what we're calling it when the arms are reaching down forever or up forever. So as x moves to the right towards infinity, which way does the arm go? Does the arm go up to positive infinity forever or down to positive infinity forever? That's what the notation here means. This says, as I move towards negative infinity on the right, which means basically, if you're looking at the graph, as you move across this way, as x is moving this way, which way is the y value going? Since this is x to the 10th, I know it has to be up on both ends or down on both ends, and the leading coefficient is positive 1. That means it has to be up on both ends. In fact, this one gets extremely flat in the middle and then goes up like this. I would not expect you to know necessarily that it's going up like that. What I would expect you to know is that on the far left it goes up forever and the far right it goes up forever, and you might not know whether it wiggles or gets flat in the middle. Now, what happens as x goes to positive infinity? That would mean as x is moving to the right, which way does the function go? Up forever or down forever? And the answer is up forever. So the answer to both of these is that the function is moving towards positive infinity as x moves to the far left, negative infinity, and to the far right, positive infinity. Now let's put together what we've learned to draw the graphs of these functions. If I want to know what the leading coefficient and the degree is, I'll take each individual factor's highest degree term and multiply those together, including any powers on the outside. In this case, I'm going to take the 3 on the far outside because it is a factor, times, in the factor x plus 3, the highest degree term is x, so I'll multiply the x. In the second factor, the highest degree term is x, and in the third factor, the highest degree term is x. That leads to 3 times x times x times x, or 3x cubed. The leading coefficient will be 3, and the degree of the overall polynomial is also 3. Because the leading coefficient is positive and the degree is odd, then I know in general it's going to look something like this on the far left and like this on the far right. My only question is, what does it do in the middle? Does it wiggle up and down or get flatter as it approaches that center point? To find that out, we need to find the intercepts. That would be the y-intercept and the x-intercept. The y-intercept comes from allowing the x-coordinate to be 0. So to find the y-intercept, I'm going to rewrite the equation and just find h of 0, which would be 3 times 0 plus 3 times 0 minus 2 times 0 minus 4, which gives me 3 times 3 times negative 2 times negative 4. That would give me a positive 72, which means that wherever it's crossing the y-axis, it's at 0, 72. How do I find the x-intercepts? To find the x-intercepts, I need to find where those factors are 0. Now the first factor is 3 by itself, but 3 is not 0. It's not wrong, it just doesn't contribute to an x-intercept. Where is x plus 3 equal to 0? X plus 3 is 0 when x is negative 3. That's the ordered pair, negative 3, 0. The second factor, x minus 2, is 0 when x equals 2. That's the ordered pair, 2, 0. The final factor, x minus 4, that will equal 0 when x is equal to 4. That's the ordered pair, 4, 0. Let's put the information we have onto the graph and see what it looks like. Bear in mind that when you do this, you're not going to get a precise graph without a graphing calculator. You won't have a graphing calculator on the test, so what you will be doing instead is drawing an estimate or a best guess of what you think it looks like. Let's put our information together. I'm going to draw a graph, a very basic graph. Okay, and I want to try to put on this information. Somewhere on this graph, way up at the top, I have the value 0.72. 0.72 came from the y-intercept. Because I'm not going to draw it to scale, I can pick my favorite spot and simply call that 72. If you label it, it is so. Now I want to graph my 3 x-intercepts, negative 3, 0, 2, 0, and 4, 0. For these, you will make some tick marks, 3, 4, 5, 1, 2, 3, 4, 5. Clearly, my graph is not to scale. So I've got negative 3, 0 on the left, 2, 0 on the right, and 4, 0 on the right. Now I need the information about the leading coefficient and the degree. The leading coefficient was 3, the degree was 3, and that means that when I'm looking at the graph, it generally goes down towards negative infinity on the far left and up towards positive infinity on the far right. So I'm going to put that piece in first. Down towards negative infinity on the far left, up towards positive infinity on the far right. Now the next piece we haven't talked about, but we should begin talking about it now. When you look at each of these factors that led to the x-intercepts, do you see that they're all essentially raised to the first power? The power indicates whether it will cross over the x-axis at that point or bounce off of it and stay on the same side. When the powers are odd, it crosses the line. When the power on that factor is even, it bounces off and stays on the same side of the axis. In this case, all three powers on the three factors that led to the x-intercepts are all odd. Therefore, they will all cross the x-axis. So now I simply connect these as smoothly as I can, crossing over in between. Now, do I know that the lowest point on the graph here is right there? No, I don't. I'm doing a guesstimate of what the overall graph looks like. Notice I have two turning points, which means that the degree has to be at least 2 plus 1 or 3 or larger. 3, 5, 7, 9, any higher odd degree. Let's do an example of one where it does bounce. I noticed there weren't any in the homework, but this is something you should know. Now, this is a much more difficult problem than the one we've seen before. Let's first try to find the degree and leading coefficient by pulling the highest degree term out of each factor with its power and multiplying them together. First, let's identify where the factors are. There's the first factor, negative 2x squared. The second factor is the x minus 3 quantity cubed. The third factor is 2x plus 5. And the fourth factor is the 3 minus x quantity squared. Now I need to identify the highest degree term in each part. The highest degree term in the first one, since it's a monomial, is the whole thing. So I'm going to use the minus 2x squared. The highest degree term from the second factor is the x by itself, but I will leave off the lower degree term minus 3. That gives me an x quantity cubed. The highest degree term out of the third factor is the 2x combined. The plus 5 is a lower degree term, so I will take the 2x with its unwritten power of 1. The final factor is 3 minus x. 3 is written first, but minus x has degree 1, which is higher than the degree 0 of the 3. So I will take the negative x, sign included, with its power of 2. When I multiply those together, I get a negative 2 times 1 cubed times 2 to the first times negative 1 squared. Let me write that here. Negative 2 times 1 cubed times 2 to the first times negative 1 squared. That number multiplied out is going to give me a negative 4. So my leading coefficient would be negative 4. Notice I have to square the negative 1 before I can multiply by the others. That guarantees a negative leading coefficient. Now what about the degree? I will have x squared times x cubed times x to the first times x squared again, or x squared times x cubed times x to the first, and since I took the negative off, the last is also just an x being squared. That's 2, 3 more would be 5, 6, 7, 8. This will be negative 4x to the 8th if I were to multiply it out. That means that my leading coefficient is a negative 4, and my degree of the overall polynomial is 8. Since it's negative leading coefficient and even degree, that means that on the far left it should go down forever, and the far right it should go down forever. I just don't know exactly what it does in the middle. Probably it wiggles. Now let's find our y-intercept and x-intercepts. Scrolling up a little bit, let me add some space. To find the y-intercept, I need to allow the x-coordinate to be 0. So this is 0, some value for y. I'm going to replace all the x's in the original equation with 0. This will give me -2 times 0 squared times 0 minus 3 quantity cubed times 2 times 0 plus 5 quantity to the first times 3 minus 0 quantity squared. The first one is going to become a 0. 0 squared is 0 times -2 is 0. The second is -3 cubed, but I'm multiplying it by 0, so that's going to wipe it out. The second one would be 5 to the first, but again, I'm multiplying by 0, and the last would be 3 squared. But the 0 is going to cause it to be 0. That means that my y-intercept is the ordered pair 0, 0. What about the x-intercepts? To find the x-intercepts, take each factor individually and set it equal to 0 and solve for x. My first factor was -2x squared, and I set it equal to 0. Since I got that 0, 0 was a y-intercept, that does mean that it is also an x-intercept. 0 divided by -2 is still 0. That means that I have that x is also equal to 0, or this is again the same point, 0, 0. The second one that I have is coming from my second factor, x minus 3 quantity cubed. I need to pull the x minus 3 out, the base factor, and set it equal to 0. The value of 3 would make that 0, so this is an x-intercept of 3, 0. The third one is 2x plus 5. If I move the 5, I get 2x equals -5, and dividing by 2, I get x equals -5 halves. That is the ordered pair, -5 halves, 0. The final one is a little bit tricky in that you have the variable coming second after the minus. You can always move the x to the other side by adding it. This gives me 3 as the final x-intercept. So now I have 4 x-intercepts and 1 y-intercept. Let's put these onto the graph. Moving up, I need some tick marks, so I'm going to make some marks. 3, 4, 5, 2, 3, 4, 5. And I know that my y-intercept was 0, 0, which also accounted for one of my 4 x-intercepts. What else did I have? I had 3, 0, which showed up twice, and -5 halves, which showed up once. If 3 showed up 2 times, that means it's a solution twice. The -5 halves would be -2.5, which is here, and the 3 would be here. But the 3 showed up an even number of times, and an even number of times means it will bounce at that point. So when I draw my graph for this, I need to make sure it goes down on both sides to take care of the leading coefficient being negative and the degree being even, and I need to hit each of these points. So I'm going to come down to the far right, or far left, down to the far right, oops, and now I need to wiggle between, but I need to bounce off of the one that showed up twice. If you don't bounce, there's no way to get it going both arms down. There's only one correct way to draw them. Now, I don't know exactly where the turnarounds are for these points, but again, I'm just trying to get a guesstimate for what the graph looks like, and this is close enough. let's look at the two graphs you see here. The one on the left, you can see that the arm on the left side is going down forever and the arm on the right is going up forever. The degree has to be odd because I have a one up, one down. The leading coefficient also has to be positive or greater than 0 because I have a down on the left and up on the right, meaning it's generally going uphill. What's the degree it could be? I've got 1, 2, 3, 4 turnarounds, so it has to be at least degree 5 or higher, but all odd, 5, 7, 9, and so on. What about the one on the right? On the one on the right, on the far left, it's going up forever, and on the far right, it goes up forever. Since they're both up, this one has to be even degree. The leading coefficient also has to be positive because they're both up instead of both down. What's the possible degree? Turning points, I have 1, 2, 3, which means it has to be at least degree 4 or higher. So 4, possibly 6, having trouble getting it to right, 8, etc. Right? Let's take a quick look at this problem where you're supposed to take an open box and construct it out of a piece of cardboard 13 inches by 13 and folding up the sides. Basically, you're taking a piece of cardboard and you're going to cut out the corners. So you're cutting out that corner and that corner and that corner and that corner. Then you're going to take and you're going to fold it on the pieces in between so that they match up, but you're going to need a lot of duct tape to get it to go together. So if they're 13 inches on each side, which mine is not drawn to scale, how can you find the volume? Well, if this side was originally 13 inches, but I cut off a little corner of X and X, then what I've actually done now is I've produced this little shape right here has to be 13 inches minus 2x. 1x for that corner and 1x for that corner. And this side right here also has to be 13 inches minus 2x. When you fold up the box and you look at it from the side, the height of the box is going to be x because it's this little measure that you folded up and it has height x. So the volume is going to be 13 minus 2x times 13 minus 2x, area of the bottom, times x. Or you could write it as x times 13 minus 2x, quantity squared.